Thank you for informing me. Good morning, everyone. So, welcome again for our last keynote of the day. And of course, I think this is the last session for our conference. Hope that all of you have been going through a wonderful journey for the past 3 days. And today, last but not least, we have our last keynote speaker, Dr. Muhammad Hazli Muhammad Zabil. I was supposed to write an introductory about Dr. Hazli, but then I figured I know him like so well. I'm trying to go impromptu this morning. So without needing to point out the obvious, Dr. Hazli is currently the Deputy Dean of the College of Computing, University Tenaga Nasional, which is a university under the ownership of the largest energy entity in Malaysia, which is Tenaga Nasional Berhad. Okay, and without need to explaining a lot, you know that under our university, we have to embark on a lot of research and innovation in energy-related matters. So Dr. Hazli is one of the pioneers working on a lot of projects with our mother company, TMB, especially on energy informatics. So that is exactly what Dr. Hazli would be sharing his insights, experience, and also inspiration for us all on the topic of energy informatics, big data, and artificial intelligence in smart grid. So I think without further ado, I'll pass the session. Let us give a big hand welcoming Dr. Hazli.
Okay, thank you very much, Dr. Lim, my friend and the chairperson for today. Assalamualaikum and very good morning to all participants. So last but not least,
Yes.
All right. Okay. How are you today?
Okay.
Okay, good. Looking forward to the closing ceremony, I guess. All right. Okay, today's topic is energy informatics. My intention is to share the emerging research areas or research discipline called energy informatics. Unless you are familiar with the energy industries, so maybe you will appreciate the energy informatics. But that's my job to give you the insight of the energy industries and why do we need this energy informatics research discipline. Okay. So some introductory. Currently I'm a senior lecturer at the College of Computing, at the Department of Computing, College of Computing, University Tenaga Nasional. Okay, and then just to point a few energy-related projects that I've involved in. Yeah, I've done we have master SCADA availability and reliability index. That's when you have your service provider. Okay, you have to make sure that the equipment and the service meet some reliability and availability index. Okay. So and then we also do, because like TMB, like Dr. Lee mentioned, TMB they have a lot of substation, power station equipments. Okay, so all of those they have SCADA system to get the status of the equipment. So we predict the failure. Software projects. Okay, there's one division, the ICT division in TMB. So there are a lot of software projects where they're given to outsource to a vendor or in-house development. And then, of course, when in software engineering, there are always problems when you have software projects. It can be over cost, okay? It can be delayed, okay? And there are many problems. So we try to predict and try to do assessment of the software projects. And then we have virtual geohazard monitoring and asset management system. So TMB has a lot of assets throughout the nation. So we try to monitor using satellite. This project is using satellite image, and we have a ground station satellite in Banting, Selangor. Okay. So from the satellite image, we can do some prediction, we can do some simulation. If there are flood, for example, which asset will be flooded, and so on. Okay. And SCADA, another SCADA project. So all of the substation, they have equipment, and when there are failure, they will try to capture the failure and notify the PIC. Okay, and currently the ongoing project, I think Dr. Lin is involved. This is 4 million ringgit worth of project. Is the main one of the main key person in this project to detect for corporate governance optimization. Okay, so TMB have a lot of subsidiaries, so we want to ensure that the subsidiaries are following the good governance. Okay, so that's among energy related projects, okay, that I just share with you. Okay, so the agenda today, I think battery is out.
Maybe here, maybe you try. Testing. Oh, sorry.
Okay. Okay, the agenda today. So I will try to give you the context of the energy industry in the world and in Malaysia. Okay, because we are in Malaysia, I will touch a bit on Malaysia. Okay, and then why there is an energy transition, we call it, and that leads to energy informatics research discipline. Okay. Okay, first, we have the electricity, this energy. Do we know where does it come from? Fossil fuels. Yes, fossil fuels. That's one energy source, correct? Renewable energy. Renewables, correct? Then is renewable water, hydro. And then we have nuclear, correct? Food. Biomass. Biomass. Okay. Thermal. Okay, and then fossil fuel, coal, gas, oil, and so on. Okay. In general, we have 7. Okay, we have 7. So this is the current energy source of the world. Okay. Unless we found one energon cube somewhere. You're not movie goers. All right. Okay, so here you can see 60% of the energy source in the world come from fossil fuel. And then low carbon, nuclear, hydro, wind, 35%. Yeah, and the breakdown here, okay, and we can see nuclear is 9.2%, wind, solar, hydro is around 18, 25, 26%. Okay. Okay, that's the main energy source. Okay, in Malaysia, okay, we have coal, gas, hydro, and solar. Okay, so we have four coal plants, 8 gas plants, 5 hydro steams, and 2 solar. Okay, so that's the context in Malaysia. Okay, now let's look at the world energy consumption. Consumption versus source. So this is the consumption. Okay. So the big one is nuclear energy. The biggest chunk here is oil, and this natural gas is coal. So these are fossil fuels. Okay. The green one is the renewable. You can see it's growing. Okay. And then the blue one is hydro. Okay. And then this is the consumption. It means the consumption is keep increasing. Okay. From 2000, the past 20 years is keep increasing. Okay. Especially now we have EV. Okay. So more electricity are needed to charge the EV. And then smart devices. Okay. Okay, that's the consumption. This is the source. So this is oil, coal, and natural gas. So this is fossil fuel. So we can see the trend is reducing, but yeah, is reducing. Okay, and we can see the renewable energy source are increasing. Okay, hydro also stable, but this one is nuclear energy decreasing. decreasing. And then we have significant decrease here around 2011. Okay. Okay. Okay, if I recap here, nuclear power is one of the low carbon fuel. And it is a favorite of developed countries. Developed countries with technology and so on, they favor nuclear power. From the 90s, okay, if I can show here, from the 1990s to 2000, okay, there are increasing interest to build a nuclear energy power plant. US has almost 100. China is developing more and more. We have Russian, we have France. 70% of the France energy is come from nuclear. Okay, okay. It is, but only certain country can use can develop this nuclear power plant, and then the reason is to get that uranium-235. Okay, that's the fuel for energy, for nuclear energy. Okay, all right. Nuclear power plant produce clean energy. It's clean and it's safe. The safest, contrary, right? Safest among, if we compare to hydro, compare to even solar, okay, nuclear energy based on data, based on terawatt hour production is the safest. So I think we can give the analogy like aeroplane. Aeroplane is the safest transport based on a number of accidents per passenger carried. So it means that it is safer to travel via aeroplane compared to via vehicle, land vehicle. Okay, based on that perspective. Okay, but the problem with nuclear power plant is the byproduct. Okay, the byproduct, the energy, the radioactive material produced, okay, when we generate the electricity. Okay, so that's the only drawback. Okay, I think another drawback is the risk. If something happens, similar like airplane, if something happens, then you just have to pray. Okay, if nothing happens, alhamdulillah, no problem. Okay, so it's the safest transport. Similar to nuclear energy. If nothing happens, it's the safest. But if something happens, then okay. Now, another part, Fukushima Daiichi. Prof. Nakamura is here. We have some friend from Fukushima, Japan.
Nakayama.
Prof. Nakayama. From Fukushima. Okay. So I think they know about this story. Okay, but this incident marked a very significant timeline in the nuclear energy industry. Okay. So Fukushima Daiichi, I said Fukushima has 2 nuclear power plants. Prof, if I'm wrong, please correct me. Okay, there are Fukushima Daiichi and Fukushima Daini. Okay, nuclear power plant. It was commissioned in 1971. So from 1971 until 2000 until 2011. Okay, 6 boiling water reactor. Boiling water reactor. Just to give you a clear picture about how nuclear power plant produce energy. So we have the nuclear reactor. Inside the nuclear reactor, we have the uranium, and then we have it is controlled by, they call it steel rod. Okay, that rod. That rod will control how much energy will be released by uranium-235. Okay, so the energy released by this uranium will produce heat. Okay, that heat that reactor need to be cooled using water. So the reactor produce heat, it hit the water become vapor, steam, the steam will move the turbine. So the turbine move and then generate electricity. Okay, it is a closed circle. Okay, so there are no carbon emission, because it produces turbine, vapor, water vapor. So it's clean. Okay, nothing happened, safe. Something happened. All right. So the water reactor of electrical generator with a combined power of 4.7 gigawatt electric. Okay, the six. There are six reactors. Okay, so that makes Fukushima Daiichi one of the 15 largest nuclear power stations in the world. One of the 15. Okay, the largest, right? I forgot lah but it's one of the largest. Okay. So ada apa dengan Fukushima Daiichi? What's with the Fukushima Daiichi? In 2011, March 11, okay, there was an earthquake known as the Great East Japanese Earthquake, around 70 km to the east of Honshu Island. Am I correct, Prof? Okay, the earthquake is very strong, magnitude 9 scala Richter, and it creates tsunami. Okay, the earthquake.
Sorry.
Okay, it creates tsunami. So when the earthquake was detected, the energy power plant shut down automatically because of this danger. Okay, so it is a safety feature. Okay, the issue is when tsunami hit this power plant. It's a very strong tsunami. I read it is 8 meters or 5 meters of water. Okay, so hit the power plant and then flooded the generator. Okay, the cooling generator. So now the reactor, I mentioned the reactor need to be cool. The reactor need to be cool, but now the cooling generator has been out of order. Okay, so we have a problem. No problem, we are safe. When we have a problem, then it starts everything at the disaster. Okay, so the accident was rated 7 on the INS scale. So there are only 2 incidents that rated 7. The first one is in 1996 Chernobyl nuclear reactor in Ukraine. Okay, and the second one is this. Between that, from 1996 to 2011, there are many incidents, but scale rated 1, 2, 3, 4 the most. Okay, but this one rated 7. Okay, so from 1971 until 2011, how many years? 30, 40 years, no incident. How many electricity generated? Just 4.7 for almost 40 years, no issue. Okay, so it's the cheapest, safest, cleanest, okay, energy source. Okay. So after this happened, so many countries, including German, even the UN, okay, they revised the energy policy. Even in Japan, they stop the nuclear power plant and make a audit, a safety audit, a stress test and so on. Okay, so in the past, I mean before 2011, Japan, 30% of the Japanese electricity come from nuclear, but after that, in 2021, it's just 7 point. So that's why we can see the declining, okay, of the energy produced by nuclear power plant. Okay, but one country that is still using nuclear power plant is China, Brazil. United States still, but still a lot more. But we have to understand that this nuclear power plant is very high tech and then very expensive. You cannot just shut it down like that. Okay, but the trend is decreasing. Okay. except for China and Russia. Okay. So now we can see here energy consumption. Okay, so I just compared with Malaysia just to give the Malaysian perspective. Okay. Nuclear is the green one. In the 90s, it is increasing, but after 2010, it is decreasing. Okay, and then we have oil. Okay, quite stable. Oil, coal, gas. This is the fossil fuel, and then the rest are renewables, solar, and so on. Okay. So from the world perspective, 1% increase in total primary energy consumption, taking it to 3% above the 2010. That means the energy keep increasing. We are using more and more energy. Okay, with gadget, with EV, with economical activities, we use more and more energy. Okay, renewables, they share the primary energy, share of primary energy consumption reached 7.5, an increase of nearly 1% over the previous year. So renewable also increased. Fossil fuel remains steady. Okay. Okay. So now, why there is an interest to increase the renewable energy? Okay, the interest is because we want to save the planet. We want to save the planet for future generation. Okay. So natural gas price increase, carbon emission record high in 2022. And this carbon emission, the largest contributor to global climate change is fossil fuels, coal, gas, oil, power plant. So when countries with coal, gas, oil power plant, for example, Malaysia, okay, majority, so we contribute to global climate change. Okay, so we want to save the planet. Okay. So fossil fuel accounting over 75% of global greenhouse gas emission, nearly 90% of all carbon dioxide. So if we can replace all of this fossil fuel energy power plant, we can save the world. Okay, we can reduce the carbon emission. Okay. Okay. So this chart is to share with you the renewable energy, the interest in generating electricity using renewable energy. It rose 14% in 2022, reaching 40.9 exajoule. Okay, electric, slightly below the previous year. The previous year was 16, and solar and wind capacity continued to grow rapidly. So interest in solar and wind. 200, so 72% of the capacity. The largest portion of solar and wind growth was in China. Okay, and hydroelectricity generation increased by 1.1% in 2022, while output from nuclear fell by 4.1%. It reduced nuclear. Okay, so why all of this matters? Energy transition. Okay, so what's energy transition? Okay, energy transition, in the layman's word, is we shift from using fossil fuel to renewable energy. Okay. In 2015, Paris Agreement under United Nations, Paris Agreement, 175 countries have ratified, okay, a legally binding international treaty commitment to reach 45% emission reduction by 2030 and net zero by 2050. Net zero means what? Zero carbon. Okay, all these 175 countries have agreed. Okay, we will try to reach zero carbon by 2050. So if we want to achieve that, we have to reduce roughly 6% every year between 2020 and 2030. Okay, and this can only be achieved by accelerating source of clean energy, renewables. Okay, you can opt for nuclear, but if something happen, again, all right. So from the perspective of Malaysia, the government has just launched the National Energy Transition Roadmap, NETR, in July 2023. Okay, and from the PME perspective, they allocated more fund for energy transition related investment. Okay, from 2018 to 2024, only 6 billion, but for 2025 and 2030, in these 5 years, 35 billion. Okay, budget for whatever energy transition related investment, okay, research, development, and so on. Okay, so that shows the commitment of the government towards this renewable energy. Okay, because of this, so we know that we have to change to renewable energy. Okay, but it's not that easy to change to renewable energy. Okay, so before we talk about renewable energy, then I would like to share how electricity is generated until it reaches here. Okay, so it starts from a power plant. Okay, and then from power plant there is a transformer to step up the voltage, and then transmitted through the national grid. In the grid, the transmission line, and then input to our local substation. Okay, step down. Okay, and then to the distribution line to our premise, whether it's residential or commercial. Okay, so this is the current setup of energy. So it is electromechanical. Okay, no means of communication between devices from here to here. So the power plant generate energy and then transmit the energy through the transmission line. No control, just one way. Okay, one way distribution. Okay, and then few sensors. There are SCADA system here, SCADA system there. Okay, but if anything happen, then it has to be the intervention is manual. They have to send technician, they have to send engineers to look and rectify the issue. Okay, and it's limited. Okay, too difficult to control. Okay, after leaving the power plant, almost no control whether it will reach the targeted resident building or previously. Okay, so if it's somewhere wrong, something wrong somewhere in between, so they need to rectify it manually. So this is the current setup. Okay, and for country like Malaysia, the assets, okay, all of these assets belongs to the national energy company, the Tenaga Nasional. Okay, more than 200 billion. The asset worth is more than 200 billion. Okay, so they can't just switch like that and then change to renewable energy. Okay, so these are the challenges. If we want to move towards renewable energy, so we have to, there are a few challenges. What are the challenges? First, the renewable energy, because in the previous slide, I mentioned about the main source of renewable energy are solar and wind. Okay, solar and wind. So the way it is weather dependent. Okay, weather dependent. So instead of supply meets demand, so it has to be supply with demand. If you have energy, if you have wind now, you have energy. So do you have demand? So we have to match the supply and demand. Okay, and then maybe at some time you have supply, you have the energy, but you don't have demand. Maybe energy at night. Okay, the wind is very strong at night. Okay, but no demand. So there is a need of energy storage. We have to store the energy. Okay. Yeah, and then uncertain supply, uncertainty of supply due to the intermittent character. Okay. Prediction of supply and demand is more difficult. Currently, okay, we know that during peak hours between 11 to 2 p.m., for example, the nation will be consumption 20 megawatts of electricity. So the TMB, okay, the utility company, they already have installed, okay, all the power plant to produce to meet that demand. Okay, but if you are using renewables, it is sunny and suddenly it is cloudy. Okay, so it's weather dependent. Okay, so we need to study the consumer behavior. Okay, new application. Then there are new applications. For example, previously, if you are familiar with clothes dryer, washing machine, and then you have dryer. Okay, the older technology is using heated airflow. Then the latest technology is using heat pump. Okay, more energy saving. And then with our air condition, previously we have conventional, and then we have inverter. Okay, and then we have EV. Okay, so the behavior of the consumer changing from time to time. Maybe seasonal. During La Nino, everybody will switch on the aircon. During El Nino, everybody will switch off the aircon. Okay? So we have to study the consumer behavior. So we need this almost real-time information. Okay, so to control the energy supply. Okay, and then decentralization. Okay, previously, energy will be produced by the power plant. Okay, but when it comes to renewable energy, wind and solar, for example, we have many setup. For example, feed-in tariff. We can install a solar panel on our rooftop and then feed to the national grid. Okay, so it is decentralization instead of centralization. Okay, there are many energy producers, not only centralized to main a big power plant. Okay, so disappearance of large power plant sooner or later, maybe in 2050, okay, we will see no more large power plant using coal, using oil, using gas, okay, leading to increased demand of flexibility. So there must be some flexibility in the centralized energy schedule. This is schedule because we have to control more. Okay, if you can see in the previous slide, currently, for example, in Malaysia, we have 12 gas and coal, so we can control. Okay, only 12, 17, 19. We control 19. But when it comes to solar, when it comes to wind, then there will be more. Okay, too many. Okay, to control. Okay, and then dynamic characteristic of power system. The power electronic, the electromechanical system, the current electromechanical system, have to be changed to software-defined system. Okay, it has to be controlled by software, to be optimized, to have more controls. Okay, smart, okay, dynamic and faster response. Okay, so we need all of this information. So from the producer to the residential area or the building, the targeted user, we have to get all information. The substation, the transmission, the distribution, have to get the information to control. If you don't have information, you cannot control. Okay? So what's the consequences? So the inherent need of energy information. So we need energy information and control network. Okay. So that we can control and decide, make decision whether we want to increase the supply or we want to store the supply. Okay. So it is necessary to discover and exploit the flexibility load. So load must be flexible. Okay. Currently, in Malaysia, I'm not sure about in other countries. In Malaysia, we have National NLDC, National Load Distribution Center, okay, in Bangsar, the MBHQ. Okay, they control the load. Okay, which power plant will be shut down, which power plant will increase the capacity and so on, they control. Okay, one point. Okay, necessary to discover and exploit the flexibility of load as related to demand and supply. So previously, companies like TMB, they use ICT for their business related operations, for customer, for staff, for business operations, apps and so on. But now you have to extend that ICT into operational power generation, transmission, distribution, okay, and real-time control. So ICT throughout the supply chain, from the production or generation to the transmission and distribution. Okay, so this requires multidisciplinary effort. So now we have to mix with power engineers, control engineers, okay, and even economics and legal. Okay, because data. Now in some places we already have smart meter. So smart meter is our data. How our consumption behavior, our behavior, consumer behavior, data. So there are legal issues as well. Okay, privacy and so on. Okay, so now is the energy informatics. So I hope I give you the perspective, the context, why of this energy informatics emerge. Okay, because of that, because of the energy transition, and then because the challenges of to transit to new energy sources and so on. Okay, okay. What is energy informatics? Okay, energy informatics is a multidisciplinary field that harnesses information and communication technology to optimize the energy system. So the energy system refers to the whole supply chain from the generation, transmission, distribution to the last mile. Okay, collecting, analyzing, using data, enhance energy production, enhance and optimize for distribution, consumption, and management. Everything. Okay. The key application include, so we have smart grid, renewables, energy integration, energy efficiency, efficient, sustainable, reliable energy, everything. Okay, all right. So the EI research scope. Okay, Jacobson in 2014 has outlined the research scope for energy informatics. Okay, so Jacobson. And this research scope has been used until now, the current researchers in energy informatics. In general, okay, there are two goals for EI research scope. One is energy efficiency. Energy efficiency will have this smart energy saving system. Okay, we do have energy saving product. For example, we have bulb from tungsten bulb to LED. So that is energy saving. We have non-inverter to inverter air condition compressor. That's energy saving. Okay, but that's not energy system. Energy saving system. Energy saving system is that, okay, if we have LED light, okay, LED light. But that LED light is not smart enough, so we don't really save energy. For example, this is the air condition for the whole building, for all the 3 and 4 rooms. It's too cold sometimes. Okay, it's too cold, and so it's not controlled. It's not smart enough to adapt with the needs, okay, of the users. Okay, so that is smart energy saving system. It's a system, not product. Okay, so you can come out with a smart house, smart building management, smart everything, okay, to save energy. And that's one part. The other part is renewable energy supply. Okay, so this is the main part. Okay, so it is about the smart grid. What is the grid? The transmission line. Okay, the supply chain from the energy production, transmission, distribution until the last mile. Okay, smart grid. So it is under the smart grid, there are many use cases, renewable energy, energy storage, electricity market, supply and demand, okay, power system, electric mobility, and then commercial, residential building and factories. Okay, all falls under that. Okay, and these are the technologies that we can use to support this. Okay, database, big data, human ACI, MIS, distributed system, security. Because we now are using software-defined system. So software-defined system, we have many security experts here. So we have to look at the security from the production until the last mile. Okay, production, transmission, distribution until the last mile. Okay, the security must be there. Okay. Okay. So from generation, transmission, distribution, last mile, okay, whether retail or corporate, retail, residential or corporate. So there are many research, there are many areas that need to be researched, need to be developed. Okay, the R&D, okay, for example, in the generation, data-driven supply demand, enabling distribution energy resources, optimizing the grid planning for supply and demand. Okay, and fault and status detection because the transmission line across the whole nation. Okay, it covers a very large area, so we need to monitor. We need to put sensors. We need to put smart sensors. Okay, and then we need to predict the asset maintenance. If something wrong, then it will disrupt the energy supply. Okay, in the distribution, okay, optimizing energy response to outage. So because outage sometimes is local, okay, only in Langkawi outage. So we have to do something. We have to predict. We have to have emergency ERT, okay, to reduce the outage. So it involves prediction. Okay, improving customer interaction. Okay, so now at the last mile, so customer interaction, customer behavior, we have to study. So if we have this data, it will help this distribution, transmission, and generation. Okay, so that's the energy informatics overview. Okay, now, okay, there is an energy informatics starts playing its role. Okay, so in the smart grid, so we focus on smart grid because smart grids is the largest component, is the largest component in the renewable energy because it involves the supply of the renewable energy. Okay, so there will be IoT, blockchain. Why blockchain is here? Because when we have, for example, in rural areas, okay, so we can install solar panel, okay, and then the solar panel can be installed in all of the houses in that village. So, and then we can create a microgrid. And then when we have a microgrid, okay, so there must be a way to have one general ledger because we want to know who is harvesting the electricity and who is using the electricity within that microgrid. Okay, VR, ER, okay, and then digital twins. So we can have an exact model. Okay, the real power plant or the real transmission line, and then we have the exact twin in digital form. Okay, so okay, now AI. Okay, so just to highlight a few. Okay, so we have in Malaysia we have started with smart meter. So most of us having this TMB, my TMB apps. So from my TMB app, we can see our consumption. So that consumption come from almost real time from our meter, the smart meter. Okay, so AMI, advanced metering infrastructure, phasor measurement. So this is the wave of the power grid. You have to manage. We have to manage that as well. Okay, and then what area monitoring? All the assets, transmission, distribution, substation, and so on need to be monitored. Okay, RTU. Okay, RTU installed in especially in distribution, all the substations. If something went wrong and so on, so we have to manage. We have to respond quickly. Okay, supervisory control, SCADA. Yeah, I mentioned a few SCADA project that we are involved in. Okay, and then intelligent electronic device. Okay, so monitor and recording status changes of the substation outgoing feeders. So from the transmission grid to the substation to the distribution. Okay, so prediction, mostly prediction, optimizations. Okay, those are the opportunities, research opportunities, okay, that we can look at. So when we want to do prediction, of course we need data. Okay, so big data analytics is smart grid. And then when we have sensors, we put sensors everywhere because we want to get the information. So we have data. Okay, so what can we do with the data? Fault detection, because we have decentralized, we have more and more generators, not only the main power plant, but the solar panel, the wind generator, and so on. Okay, transmission stability analysis, okay, supply and demand, electric device state estimation, health control, health monitoring, transformer distribution, substation, equipment in all of those assets, And power quality monitoring as a worldwide issue, electric power quality refers to the magnitude, frequency, and wave form of voltage and current in power system. Okay, so we have to monitor. Okay, and if something wrong, then the provider have to do something quickly. Okay. The topology identification. This is on how do we plan the smart grid layout. Okay. Renewable energy forecasting, of course, because it's not consistent. Okay, it is so we have to predict. So we need data from weather, meteorological data, and so on to predict. Okay, the sun to predict the weather, and so on. Okay, load forecasting. This also related to the consumer behavior, and load profiling the consumer behavior. Okay, load aggregation. Okay, non-intrusive load monitoring to segregate, okay, the overall load profile. So maybe some area needs more supply, some area needs less, so we have to manage it. Okay, non-technical loss detection. So non-technical loss detection means throughout the transmission from the generator to go through transmission and distribution, there will be loss. Okay, so we have to optimize that as well. Okay. Okay, so this is just one example of how the energy informatics contributes to optimize, to make the tomorrow energy system better. Okay, so we have data from equipment condition, the meteorological environment, the consumer behavior, the smart meter. Okay, so we have to clean the data. Okay, we have to do the analytics, and from the analytics, the provider can decide whether to increase supply, reduce supply, distribute the supply, and so on. Okay, so this is an example of how energy informatics contribute, okay, to the energy system. Okay, challenges and ethical consideration. Like I said, there are legal aspects as well, because we are collecting data, consumer data. Okay, data quality and availability. So all this big data, prediction, and so on relies on high quality data. Okay, in some region, data on energy consumption, whether the weather patterns, renewable energy generation, limited or unreliable. So we have to look at it. Okay, interoperability. Okay, so integration of AI system into existing energy infrastructure. So we have the energy infrastructure, the current infrastructure. We cannot just simply scrap it or shut it down, the power plant. We have to integrate the new RE generation and the system to the existing. Okay. Algorithm bias, particularly concerned with we implement AI in energy program that affect different social economic groups. A rural area, perhaps different behavior. In the city center, different behavior. Okay, maybe more on in the industrial area. Okay, different. Okay. So the algorithm must be smart enough to differentiate this. And then complexity and scale, regulator hurdles, okay, because of the regulation and public acceptance. Okay, so public acceptance also, for example, when TNB deploy the smart meter, okay, they deploy first in Malacca, one of the state in Malaysia, small state, okay, for a test. And then there must be a public acceptance because their data are collected, how they use electricity are collected. So ethical consideration. Then we have a privacy, security council. Okay. Yeah, ethical consideration again, privacy, transparency of how the algorithm works. Okay. Public wants to know the decision made by the system to reduce or to increase the supply. It has to be transparent because it's national interest. Okay, it cannot be a black box. Okay, equity. Okay, accountability. AI decision to address potential errors. So, because it's national interest, if something happened to the electric supply, then it affects the whole nation. Environmental impact also. Okay, long-term viability, ensure the AI system that we design and use in the new energy system, okay, sustainable and adaptability, because there might be changes. Okay, human oversight. So when AI can automate many tasks, okay, there should be human oversight to ensure ethical and responsible decision making. For example, previously, we have technicians that go to one house to another to read the meter. Okay, thousands of meter readers. When we have a smart meter, there's no need of this job. Okay, so the provider have to also consider this issue. You cannot just throw in people like that. There must be some kind of reskilling, upskilling, okay, of the the human workforce. Then data ownership. Who owns the data? The provider is my data, okay, my consumption behavior. But who owns it? Is it the provider? So these are the ethical consideration. Okay, cultural and societal consideration. And implementation should consider cultural and societal value to ensure acceptance. Okay, acceptance. Some people, they are very particular in terms of data. Yeah, I don't want to use a smart meter. I don't want to use this smart application, or because it gets my data, it keeps my data, it uses my data, so on. Okay, so all of these are challenges, all right? Okay, lastly, okay, because we start with the Earth, the Mother Earth. So I end with also how this AI, how this new energy transition helps in battling the climate change, because the current energy generation approach or practice, it produces the most CO and carbon emission. So we have to do something to save the Earth. Okay, so with AI and data analytics, so what we can do? Okay, so we can models will become more accurate. We have to have a better and accurate, more accurate models. So energy production can be the production and the supply and demand can be very optimized. So there is no wastage. Okay, there's no wastage. And then renewable RE optimization. So AI algorithm improve the efficiency of the solar. So solar need to be maintained. Okay, the solar panel, the wind turbine also need to be maintained. So there must be some way of how AI can optimize this. Okay, grid management. Grid is a transmission and distribution line. Okay, so because we have more energy producer, the solar on the rooftop, feed-in tariff, and so on, and then decentralization, it has to be managed. It has to be managed. And then energy efficiency in building. So, like I said, if we can make a better system, energy system, it will reduce cost, it will reduce the energy consumption. Okay, based on historical data, energy consumption has been rising from year to year. And carbon capture and removal. AI will be used to develop more efficient and cost-effective carbon capture removal technology, so helping to reduce the greenhouse emissions. So if we can monitor, if we can detect, then we can do something about it. If we cannot monitor, we cannot detect, okay, then less control on it. Okay. Okay, so for conclusion, so energy transition towards renewable energy marks the starting of the new energy system. Okay, new energy system. We need to come up with a new energy system to replace the current energy system. Because the current energy system cannot cope with the RE. There are challenges if we want to use RE. Okay, so and it involves multidisciplinary effort, not only from computer scientists, not only from information system, but also from power engineering, control engineers, and so on. Okay. And then ER become the main enabler towards efficiency, load flexibility, and resilient decentralized system. Because there will be many solar panels, many solar farms, many solar on the rooftop. So all of those become the harvester or the producer of the energy. So have to be managed. the new energy system must be reliable. So the current energy system is reliable, correct? The existing one is reliable. We can depend on it. Okay. Seldom nowadays we have an energy shortage. Okay, or outage. Sorry. Shortage and outage. Okay. So the new one must be as reliable as the current one. And it has to become none other than not less than better. It has to be better than the current approach. Okay, the current practice and the current infrastructure. Okay, so with that, I hope I give you some insights on what is energy informatics and what are the research scope that we can embark, okay, and we can explore. Okay, hopefully this will give you idea. So from cyber security, data analytics, AI, okay, how we can contribute to make our energy system better for tomorrow and save the earth. Okay, with that, thank you very much.
Thank you very much, Dr. Hasbi, for such an inspiring talk on energy and planet saving. So I think we have it took quite a long time actually. Really? Yeah, that's good. So and we are still very engaged. I believe we still want to listen more. We can have a couple of questions. So yes, please.
Thank you. Hello, sir. This is a pretty interesting topic, and actually, this is also my field of endeavor currently. So, yeah, a renewable energy or green energy keeps on increasing, and it's a good thing to achieve the zero carbon emission and also to decrease the world temperature. I think the goal is to reduce by 2 degrees Celsius. So, yeah, it's good, but currently we are too focused on the forecasted renewable energy generation, right? And also to the energy generation to be produced. But is there any existing method or programs to manage the wastes from the renewables? And the other part of the question is, have you seen any specific involvement or application of energy informatics in managing these wastes?
Okay, thank you, Prof. Waste from energy, renewable energy.
Actually, it's like a general.
Okay, one of the energy source for renewables, I think the waste is the most significant, the most dangerous waste is the battery. Okay, because battery is using lithium ion, and when the lifespan over, then you have to dispose it correctly. I don't have that information. Okay, how we manage that waste currently. Yeah, electronic waste, e-waste, and then but electronic waste not directly related to RE. Okay, but I think battery is the one that related to RE, and how we dispose our handphone battery, our laptop batteries. Even now with EV, so we have to think about how this. There is one issues raised when there are more EV on the road. That means we produce more batteries. But to produce batteries, it involves getting rare earth element, okay, rare earth RE, rare earth element, and to dispose is also trouble. Okay, if it is not well managed. So I think there is also a country level or maybe world level policy that needs they need to have. Just to compare with nuclear energy. Okay, nuclear energy produce radioactive waste. Okay, so what these developed countries they have they designated an area to store all of this radioactive waste. First, they put it in water. After a certain area, they will put it in a concrete container and then put it in somewhere. They call it radioactive waste. Okay, they store the waste there. Until how long, we don't know. If something happened, also we don't know. So far, nothing happened. Okay, but I think the same thing also have to be considered for managing the RE waste like battery. For if your question whether I've seen any so far, not yet. Thank you. I hope that my answer satisfies you.
Thank you. At least, sir, you have an idea with the nuclear, and for solar, I think there is no like regulations yet.
Yeah.
Because for example, batteries right now is getting cheaper and cheaper, but the end of life of these batteries is getting shorter and shorter. And what are we going to do with those if we don't have the management?
Yes.
Yeah,
Because now we have, for example, we have variable. So variable is using smaller batteries, and lifespan is maybe 1 year or 2 years. After that, you have to change the battery, right? Then you have to dispose the old batteries.
And also the solar panels.
Solar panels, the solar panel filler. Okay, solar panel filler. After certain, after the lifespan ends, then they have to dispose the solar panel. And how to manage this disposal?
Thank you, sir.
Thank you for highlighting.
Based on your experience as project leader or the one handling the projects on energy informatics and other ICT related to energy. Based on your experience in Malaysia, what would be the challenges you encountered when you face the different stakeholders, like for example, the government, industry, contribution activities, different people. Based on experience.
Okay, challenges with different stakeholders. I think this is a bit general. When we develop a system, then we talk to different stakeholders. Requirement changes every time. Every time there's a meeting, then we will have a new requirement. So we have to manage that requirement. Based on my experience, because our projects directly with TND, so the requirement come from TND. Okay, and but in TND itself, there are many stakeholders, the division and so on. So sometimes we produce a solution without taking into consideration how it is being done before the system. Okay, just to give you an example, for the other system. Okay, so they manually check and rectify faults. When there are faults, they will send people like the current situation. It is manual. You have to send people to rectify, to repair, and so on. But the schedule is different. The work practice is different. But when we have a new system, okay, so it will change the practice. Then there are reluctance. Okay, not really accepting the new process and so on. Those are among the challenges. That means it has to be the awareness, and then it have to be, we must have a buy-in, okay, from the workforce to accept these new changes.
Thank you.
Lastly, I have two questions. First one, the mentioned about the correct me if it's wrong. Now it's probably the only power or electricity provider or distributor in Malaysia, particularly for residential connections. My question is, what is your opinion about the monopoly structure of energy business in Malaysia? Will it be a better tomorrow if we break or change the today's monopoly energy supply landscape in Malaysia?
Okay. I'm not in position to answer on behalf of energy, but based on the question is in my opinion, right? Correct. Yeah. So energy is, from one perspective we say, monopoly is not good. Okay? We must have competition and so on. that happens in automotive industries, in telecom industries, okay, and so on. Okay, but we have to look at the national interest as well. Okay, if, for example, but I will correct you. TNB is not the sole energy provider in Malaysia. It is sold in Peninsular Malaysia. In Sabah, we have Sabah Electricity, and in Sarawak, we also have SASB. There are companies under different state government. Okay, for Sabah and Sarawak, different. Okay, for Peninsular Malaysia, yes. Okay, it's number one. But moving forward, we also have, like I mentioned, decentralization. Decentralization means that now we already have a feed-in tariff. Feed-in tariff means you can install a solar panel on top of your roof and you become the provider as well. Okay, you become provider. So Tenaga Nasional is no more the only electricity provider after this. Okay, but to break the monopoly, I think because although Tenaga Nasional is a private company, but it is owned by the government because of the national interest. So there must be a balance now, because previously there was a study done, I think in late 90s or middle 90s, something like that, to break the energy monopoly. Okay, to open, they call it to open the energy market. Okay, after the study, the government decided not to proceed with that. But then there is another study, and they will study before they open the energy market, whether to allow external investors to provide. And then although we have IPP, independent power provider, but those IPP are supplying the energy or supplying the power to TNB and controlled by NLDC, National Load Distribution Center. Okay, so I think there must be a balance. If we open, then our national interest might be at stake. Okay, so one big company, just for example, Elon Musk come and create a company, energy company. So and then he can freely fire everybody in Twitter. Or you fire, then we also don't want that. It creates instability. Okay, so there must be a balance between open market and the national interest.
And the other question is about the nuclear power, nuclear energy. Based on your observation, which Asian country is actually probably the most potential of maybe nuclear replacement?
China, of course. China already have many. Southeast Asia. I heard Malaysia wants to study nuclear energy. I heard that. But just study. Okay. I don't know. Maybe I'm not sure. This is because of the risk. But yeah, we don't know. I did not study enough on this. Whether which countries, Southeast Asia countries who are interested to venture into nuclear energy. But Malaysia, yes, we do have suggestions that we go into nuclear energy. But I'm not sure whether the government will take that, because of course there will be resistance. Okay, Dr. Maha, where are you from, Dr. Maha? Kedah. Which place?
Alustar.
Alustar. Let's say we want to put one nuclear energy power plant in Alustar. Will you agree?
Well, you mentioned about consumer behavior.
Yes.
To study about acceptance of people.
Yeah. Yeah, correct. So there may be resistance. There must be a lot of buy-in from the government. There are a lot of things. Okay. But still, based on data, nuclear is still the safest, cleanest. But the only thing is, one is the risk, the second one is the radioactive waste. But for the Paris Agreement, they also in the Paris Agreement also they pledge to reduce the dependency on nuclear energy. Although it is cheap, surprisingly, I read and I saw nuclear energy is cheap actually compared to coal, compared to fossil fuel, even compared to RE, because the uranium is very energy dense. 8 mg or 8 milligrams can produce a lot of maybe 1 week of energy, things like that. It's very cheap. Okay.
Perhaps I can build in a bit.
Sure.
I'm not in a position to answer the question, but then the last question is something that we've been talking about. Is I think back in 2018, 2019, our CEO has given a speech back in University of National. It's a policy issue. It's a policy issue from a national interest point of view. But according to the CEO, if let's say it's allowed and it's feasible and safe to run an energy plant installation, we are ready and that is a comment, not an argument. So next question.
Thank you very much for something for the enlightenment. According to the Paris Agreement, the reduction of emissions is by 45%. So for Malaysia, where would this 45% come from? Where do you, or what would be the most strategic factor?
Oh, that one we need to read the NETR, newly drawn NETR, but the direction is to move towards RE. No, the direction is to move towards renewable energy. 45% from the overall, because currently more than 80% or yeah, almost 70%, I think more 60 to 70% of our energy source is coal and gas, fossil fuel. So they want to reduce this and then move towards now we can see that more and more solar farms are being built even by TNB. Okay, maybe if I can share. Okay, here solar plants. We have by end of this year we have one more solar plant, and hydro we have one more. So the reduction is there. I mean they plan to build more RE power plant to reduce carbon emission. Even TNB pledge in our diaries every year we get net zero by 2050. Net zero by 2050. Okay.
All right. Thank you. I think I have other questions. Maybe we have one before we have the closing session. Oh, okay.
The power system is getting into a status of getting more electronics so that electronics dominated power. So that means the dynamics of the power system changes. So perhaps do you have any ICT related dynamics that would address the emerging power system wherein you have more power electronics due to the
Okay, thank you for the question. So maybe I can share again maybe this slide. All right. So because we are moving towards RE, so the way we handle RE is not similar to the way we handle the current energy source. Okay, current energy source, we build a power plant. We know this power plant has this capacity, A capacity. We build 10 power plants, A capacity plus B capacity plus C plus D plus E, then we have total energy capacity. Let's say 200 or in Malaysia we have 28,000 megawatts, if I'm not mistaken. Okay. So that's the consumption of the country currently. So that power adequate or enough to supply the energy throughout the peninsula. Okay, so when it comes to RE, there are many challenges as I highlighted. Okay, uncertainty, okay, weather dependence. So prediction, optimizations are among the things that is important. Okay, because like I said, instead of in terms of supply demand, we have to make sure when there is a supply, there is a demand. Supply with demand. There is supply, there is a demand. If there are supply no demand, it will go wastage. Okay, it will waste. Or to overcome that, it has to be stored. Then we need energy storage technologies. Currently, the only energy storage technology is battery. Okay, but how big the battery that we need? Okay, and so on. So those are the things that can be researched. And then it goes to two sides, from the provider point of view, as well as the consumer point of view. So consumer also, we have to study the consumer data, okay, and then predict the consumer behavior. Okay, because once we have the information, we can plan earlier. We can plan ahead, maybe not too early, but even a real-time information, it will affect the real-time decision. Okay, whether to increase or to reduce or to distribute the supply to other places. Okay, so all of this needs systems. Okay, this system it cannot be just one isolated application or system. It has to be a system in the energy system. The energy system must be ready for that. Okay, currently all the solar farms, they still fit to the national grid. Okay, the transmission, NLDC lah, the load NLDC, National Load Distribution Center. Okay, they feed and then the LDC will try to distribute the load to where? Okay, to all the distribution and substations. So all of this need the touch of AI, the touch of big data, because when you want to predict, you need data. So data need to be collected. How do we collect data? Then we have to install more sensors, smart sensors, not only sensors. Currently, they already have sensors. We sensor in substation, in TMU, okay, at the distribution. In our housing estate, we have a few PMU, right? The building, the TND building. Okay, so there are equipments there. There are sensors, but it's not smart sensors. You have to be upgraded, and then there must be maybe to the end of some robotics. Okay, if the things can be rectified, okay, remotely, maybe we can send some drones there to do something. That is an area to be explored. Okay, thank you.
All right, thank you very much, Asli. So I think if more questions, I think you contact us, Asli. If you more
And Dr. Lim as well.
Asli at Newton, but if you don't like, that's okay, so I think maybe one round of applause, one more round. So I think we will just proceed straight to the closing ceremony, because I think this is the most important moment for you all. We have here some best people award, so we shall see. We shall see. So without further ado, we will invite our program chair, Prof. Lau Sian Lun, okay, to give away the awards for this conference. So over to you.
Right. Being between you and lunch, I have to do it very fast. Okay, so we're very happy to have selected 9 best papers. All right, and it's based on the review score that the authors have obtained. So I'm going to start with the most exciting one, postgraduate symposium, because I think some of us, or if not most of us, have gone through that phase. It's very important during the postgraduate time to get this opportunity, to join, to present, and to learn. So the best paper for postgraduate symposium. Wait, do you need to stop the live stream? Okay. Stop.